You are now starting the second part of statistics. And before I actually jump into the first lesson, I want to talk about my choice of starting this course with this topic, the Poisson distribution. If you look at the textbook, you will see that this is not where it starts. This is actually the last chapter. But I want to start with the Poisson distribution for two reasons. The first is that the last thing that you've learned last year were the distributions. You started with a binomial distribution, then the geometric distribution, and you ended with the normal distribution. So I want just to continue that flow and start this school year with the only distribution that you are going to learn in statistics 2, which is this one, the Poisson distribution. There's also a second reason why I picked this, and this regards some information that you need to have that you don't know yet, and you learn in Pure Math 3. In my own course that you have access to, you are going to see that this is in chapter 3 in Pure Math 3. So it takes a few weeks for you to get there, and I wouldn't want you to be dependent on what you learn in Pure Math 3 to understand content on statistics 2. In this topic, there's nothing that you need to learn in order to understand the distribution. There's one specific thing that probably you already saw. That's the Euler's number, the E. But all you need to know about that is how to press it in a calculator. There is nothing else you need to know about that. So these are the two reasons why I picked the Poisson distribution to start statistics 2. And now that I've got that out of the way, let's start with the actual lesson. So we're going to start with the modeling of the Poisson distribution and how can it be applied, in what circumstances it can be applied. I created this small table that you can download in your resources in the course. It tells you lots of things about the different distributions that you've learned, the binomial, the geometric, and the normal distribution that you learned last year, what X represents, the conditions, the parameters, and an example. And the circumstances in which you can use the Poisson distribution are these. You have a random variable X, and it represents the number of events occurring within a fixed interval of time, of space, of area, of volume, etc., provided that these conditions are met. I'll talk about the conditions in 1 second. Let me tell you a very few and simple examples on situations in which you could use the Poisson distribution. Imagine that you are measuring the rate at which cars are passing in a very busy road. So you can set X as the number of cars that pass in a fixed interval of time in that road, let's say in every minute, okay? You could also set a random variable X modeled by a Poisson distribution if this could be the number of, let's say, something regarding a volume, the number of insects, for example, that you have in a certain volume of space, okay? So you can see here different examples in which the distribution can be used. But besides that, you have to pay attention to these conditions. First, the events occur at random, completely at random. The events occur independently, so what happens before doesn't influence what happens next. And the events occur at a constant average rate, which is given by this Greek letter, the lambda. Okay, this is going to be very important. This is going to be the sole parameter of the Poisson distribution. Okay, so regardless of the interval of time, space, volume, etc. that you are looking at, the average number of events happening there stays the same and has this value lambda. Okay, so x is modeled by the Poisson distribution with the parameter lambda. Okay, it is the only parameter, so this makes the Poisson distribution a very simple distribution to work with, mathematically speaking. So if x represents the number of events in the given interval, lambda will be the mean number of events in that interval, and the probability that x equals a certain value r is given by this expression. E is the Euler's number. Okay, you never needed to use it, as far as I can tell, until now, and you don't need to worry about that. This is a number the same way as pi is a number. You can just go to your calculator and press it there. Okay, so the probability that x equals r equals what? Equals to e to the power of minus lambda. Don't forget what lambda is. It is the only parameter of the distribution, times lambda to the power of r divided by the factorial. I was missing the word. The factorial of r. Okay, this is what you need to do for whatever value that r can have, from 0, 1, 2, 3, 4, etc. All right. What is the shape of a Poisson distribution? It's going to be something like this. All right. As you can see here, as the value of lambda, as the value of the mean increases, of the parameter increases, this is going to get closer and closer to a shape that you are already familiarized with. If you look at this looks like the normal distribution, right? More on that later. Okay. So the thing that you need to keep in mind is that the higher the value of lambda, the closer this is going to be symmetrical. For smaller values of lambda, this is going to be skewed. Okay? As usual, if you want to calculate the probability that x is bigger or equal than a certain number n, then this is going to be 1 minus the probability that x equals 0 plus the probability that x equals 1, and so forth, until the probability that x equals n minus 1. In situations where you have lots of probabilities to calculate, there is a small mathematical trick that you can use to speed things up. This is called the recurrence relations, and allows the use of the term obtained previously to work out the next one. It simplifies calculations. Look at this, and I'm going to use an example with r equaling, for example, 3. Or I'm going to put a higher number because this is when you are actually going to use it. Let's say that r equals 10. So if you want to calculate the probability that x equals 10, and you already calculated before the probability that x equals 9, so what do? You just do lambda, which you know is the parameter of the distribution, divided by 10 times the probability that x equals 9. This value you already have, so you just have to multiply the previous probability that you calculated by lambda over r. Make sense? And you can do this recurrently until the probability that x equals 0. So imagine that you have to do that. You calculate the probability that x equals 0. Then for the probability that x equals 1, multiply the first one by lambda divided by 1, so just lambda. Then the probability that x equals 1 by lambda divided by 2, and so forth. Okay? This simplifies the calculations a lot. One last thing. You probably heard me saying a little while ago, and called lambda the mean. That's because the lambda is exactly the expectation of the Poisson distribution. More than that, it is also its variance. As I told you, lambda is the only parameter. So in a Poisson distribution, the mean is equal to the variance, which is equal to lambda. So the expectation of x is lambda, and the variance of x is lambda. As I told you, the Poisson distribution is actually a very simple distribution to work with. So you are now going to start solving exercises. As usual, this may seem a lot of theory, but you can trust me when I say that this is actually very simple to use. This is even simpler. The expectation is the variance, which is the sole parameter of the Poisson distribution. If you understood the binomial, the geometric, and the normal distribution last year, you are not going to have any trouble whatsoever understanding this one.